Hello and welcome to this video about proving theorems in linear algebra. In this video we'll prove this theorem about change of basis matrices, which double up as change of basis linear transformations. This proof looks complicated to state, but we'll provide a bit of background knowledge during this video to help break it down and understand what it's asking us to prove. I decided to break this theorem up into three parts because the last part of the proof needs these other parts of the proof. It seems easier to break up the proof into parts and prove those first. The textbook didn't give a proof of this theorem and left it to the reader, but it did leave some hints as to what needs to be proven. So I decided to prove this first, that if a matrix multiplied by any vector gives the zero vector, then this matrix must be the zero matrix. So now to prove this part of the theorem. If the matrix A multiplied by any vector gives us the zero vector, then this would include multiplying it by the standard basis vectors E1 to En. I'll just give you a look at what the standard basis vectors are. They are column vectors that are 0 in every location, except in a particular location where it is set to 1. We can then pack all of these equations up into this matrix equation, and we'll use this column vector notation using long vertical lines that show that these vectors occupy the columns. Then we can fill these matrices with the entries that they contain. And we can rewrite this matrix equation as this smaller equation down here. The matrix made up of standard basis vectors will become the identity matrix, and the matrix made up of zero vectors will be the zero matrix. And so the identity matrix may be eliminated, giving us this equation that says that this matrix A is the zero matrix. So now to prove the second part of this theorem, which says that if two matrices multiplied by any vector will be equal, then these two matrices will be equal. The vector that they multiply must obviously have the correct dimensions. So now to prove this statement, we can manipulate the above equation to get this equation. Then we can perform this factorization. Then we can use the first part of this theorem to say that this matrix quantity is 0. We can then manipulate this equation to be this, saying that these two matrices must be equal, and so this proves this part of the theorem. So now let's look at some background information so as to learn some concepts, so as to ultimately prove this theorem. We'll look at this basis set of vectors called F. This is what F contains. And because F is a basis of vector space V, it must span V. We can write this out like this using this simple formula. We can set a vector x to be this in terms of the basis vectors in F. We can define this notation to get the coefficients of this vector in terms of the basis vectors in set F. I know that there isn't any ordering in a set, but we could assign an ordering to this set of basis vectors, maybe by labeling them in some way or writing them in a set so that they have an order. We'll give this set a property that these vectors are ordered, so that F1 is the first vector, F2 is the second vector, and so on. Then this will give us an order with the coefficients, so that A1 will be the first coefficient and A2 will be the second, and so on. We can assign a transpose function to this row vector of coefficients, so as to change it into a column vector, so that it can be multiplied by matrices on the left. So this is what this transpose function does to this vector. It changes it from a row vector into a column vector. So we'll explore this notation a bit more. We can plug this value of the vector x in terms of the basis vectors in F into this operator like this. And we can plug this set into the place where the basis vectors have to go. And this will give us a row vector with all of these coefficients in it, with a transpose operator at the top. And then finally we'll end up with the column vector of coefficients that we want. And then we can have a second set of basis vectors over the same vector space V, called curly F. And this is what it will contain, lots of vectors that are denoted by small f's in running writing. And this set of vectors will also span the vector space V, because it's a basis of V. And the same vector x that we worked with before will have a different set of coefficients for this set of vectors, and they will be B1 to Bn. And applying this operator to this vector will give us a row vector containing these coefficients. in this particular order. We're assuming the set of basis vectors has some order, so that the coefficient of the first vector in the set will be the first scalar in this row vector. And then we can apply the transpose function to this vector so that it can become a column vector. So then there's a change of basis matrix called P that changes the representation of X from one basis to another. And this is what P does. It changes the basis from F to curly F. And this is what we get when we substitute the coefficients in. The first column vector contains the coefficients for F, and the second column vector contains the coefficients for curly F. So I'll just make some more room on the screen like this. So there's a matrix A that represents the linear transformation L. It takes a vector in V and multiplies it on the left to give a vector in W. And this is the basis for the new vector. It's called G, and it contains all these vectors. And this is the equation that describes what matrix A does. Lx is the linear transformation L applied to X, and is itself a linear combination of these vectors in the set G. We can use this bracket operator to get these coefficients of Lx in terms of the basis vectors in set G. And we can take the transpose of this list of coefficients to get this column vector. So I'll just make some more room on the screen like this. So this is what multiplying the matrix A by the column vector of X looks like. It gives us all of the coefficients in basis F multiplied by A, which gives us the coefficients in the basis of G. And there's another matrix B which acts on a column vector in the basis of curly F that gives us this equivalent linear transformation L of X in the basis of curly G. And these are the vectors in set G, which are small curly G vectors. And this is what the coefficients are of this vector multiplied by matrix B. So we'll multiply B by a column vector of these coefficients like this, which will give us a column vector of these coefficients that are for the basis of curly G, because they are for a vector in the codomain W. And there's a change of basis matrix Q, so that it changes these coefficients from G to curly G. And this is what this equation looks like if we substitute this linear transformation L for vector Y. I'll just move a lot of stuff up and off the screen so as to make more room to write more stuff. We can write this equation in terms of the column vector of these terms representing vector X, and these coefficients in the column vector are in terms of the basis vectors in G. And this is what the resulting column vector is after being multiplied by Q on the left. It contains the coefficients of Lx for the basis vectors in curly G. And here's a diagram that could show us this formula so as to get a quick idea of what's happening. As we follow two paths around this diagram, we can get the equation down below. So now to prove the main part of this theorem, that given all of this information, then this equation is true. We've already studied what all of these definitions mean, so now we're ready to prove it. So now we'll start with the right-hand side of this equation, multiplied by this column vector that contains all of the coefficients of X for the vectors in the basis of F. We can arrange the brackets like this so that P multiplies X more directly. I'll just make some more room on the screen. We can get P to act on X so as to change its basis from F to curly F. We'll rearrange the brackets to get B to act on X. And B acts on X to execute the linear transformation L and to change the basis to curly G, which corresponds to curly F. So now we can apply the inverse of matrix Q to X to change its basis from curly G to G, which matches the definition of Q, which changes the basis from G to curly G. And we can substitute A in to stand for L when in the basis of G, and the basis of X changes to F because it's the basis that describes X, whereas the basis G describes Lx. And so we can make this statement that these products are the same for all of the vectors in Rn. And we can invoke theorem 3.8 to say that this is enough to say that these matrices are equal. So that's it, we've proven the theorem. So I hope that this proof has made sense to you and that you found this video to be helpful. Please click like and subscribe if you did. Feel free to share this video and to post helpful thoughts in the comments. And thanks a lot for watching.